All right. Your radio observations have come back, and with them comes some preliminary data products. These are generated by Green Bank Observatory. You can get to them through Skynet. So I'm going to show you how to get to them and explain what each of them mean. And this will give you an idea of whether your observation completed successfully or not. If not, you may want to resubmit it. Okay, so you go to My Observatory, you go to Radio Observing, you find your observation, and then you go to that page. And before the observation completes, there's nothing here. But once it's completed, you have two things. You have this box right here, which takes you to Green Bank Observatory's preliminary data products. And then you have this series of boxes down here under Radio Cartographer. That's Skynet's algorithm for taking the data and turning it into images, which, if you think about it, is pretty cool. These radio telescopes are observing the invisible universe. And between this video and the next video, we're going to learn how to take the collected data and turn it into a picture that we can see, a picture of the invisible universe that is visible to us. We're going to make the invisible visible. Okay. But first, let's go to Green Bank's page and look at these data products. And I have two sets up here. This is an observation of 3C274, that's Virgo A. So this is one of our calibration sources. And then over here, this is an observation of Jupiter, which is a very faint source. Jupiter is faint, and I'm shooting this video both for Module 1B, where they looked at the moon and a calibration source, and for Module 1C, where they looked at Jupiter and a calibration source. So of these, Jupiter is faint and a little bit different, but the moon and the calibration sources are all quite bright and should look like this. Okay. The first thing you want to look at is not these two top charts, but this one right here. This is the path map. Remember, we're dealing with a 1 pixel camera. This telescope effectively, if you want to compare it to an optical telescope, has a 1 pixel camera. So if we want to map a part of the sky, we have to move the telescope around, move that 1 pixel around, and collect data. And we're doing this in a raster pattern. And this particular one is it's rastering in right ascension, going left and right and left and right. Though there's also the option to go up and down in declination. It's up to you. This one was completed in right ascension. And you just want to make sure that it looks okay. This one looks great. Even the turnarounds are really clean. Sometimes the turnarounds are not clean. As the telescope's moving along at a good speed, and then it's commanded to stop and go back in the other direction. And if this happens too quick, it's like driving down the highway at 60 miles an hour and throwing it into reverse. It's not pretty. So sometimes the turnarounds can be pretty messy. But as long as it's clean in the middle, that's all that matters. There are other weird things that can happen. If this doesn't look anything like this, if it looks like really skinny one way or the other, it messed up the mapping, and you're probably going to have to redo the observation. Or with the moon observation, since these were time sensitive, you can probably get a replacement observation from one of the other teams. But hopefully it looks like this or something like this. Okay. Now, the next thing we want to look at are these two plots up here. And they are counterparts of one another. As the telescope's moving along, it's collecting data through time, and each time it collects a full spectrum, data at a whole bunch of frequencies. So the first plot is showing you how bright, whatever the telescope's pointing at, how bright it is as a function of time. And you may ask, at what frequency is it plotting this? And it's all of them averaged together. So in this first plot, it's averaging all the frequencies, the brightness measurements at all the frequencies into a single average value, and it's showing how that's changing with time. In the second plot, it's doing the opposite. It's showing a spectrum, how bright it is at each frequency. And you may ask, at what time is the spectrum? It's at all of them averaged together across the entire duration of collecting the map, averaging it all together in each spectral channel. What's the spectrum look like? Okay. Well, first of all, I should say, or you should see, there are two curves in each of these plots. So let me explain that. At the receiver of the telescope, you have the dish, you have the receiver. In the receiver, we have not one, but two detectors. They're just metal bars, essentially. And the two metal bars are perpendicular. Let's say it's like a plus sign. Then light waves that are coming along like this will be detected by this one. Light waves that are waving like this will be detected by this one. And if it's waving at some angle, they'll be detected by both of them in different proportions. And this is so we can measure polarizations. You know, if one polarization is favored over the other, we can measure that. We're not going to measure that in modules 1B and 1C, but later on in the MW sequence, we will measure polarization of pulsars in the radio. For us, it's at this point, it's just a redundant data set. We have two detectors. Most of this light is unpolarized, so both detectors are detecting essentially the same thing. And so it's redundancy. Sometimes one detector goes down, and then we have a backup. Now, in this case, we have data on both channels, both polarization channels. So we have two curves in the light curve, two curves in the spectrum. Okay. Now let's see if we can understand the pattern here in the light curve. First thing, well, don't worry about the spike at the beginning and the spike at the end. I'll explain that in a minute. But just look at the background pattern, up, down, up, down, up, down. What this is the back, forth, back, forth, back, forth. Maybe the sky is a little bit brighter on this side, a little bit dimmer on this side. So as I go across, it goes up, and as I come back, it goes down. I go across, it goes up, and I come back, it goes down. And that's your background pattern. Now, when you run across a source, there's a source here in the middle. You can see it over here. When you run across it, the intensity increases. And so here this is 3C 274, Virgo A. First time I cross it, I get a little blip. But then I get higher up, closer to its center, and I get a bigger blip and a bigger blip. Every time I cross it, a bigger blip until I'm crossing it at its center, and then I'm above it, crossing it, and it's getting fainter and fainter. So this is a source just chopped up, slice by slice by slice. It's a bright source. If we look at Jupiter here, Jupiter is a really faint source. So good path map, and we have kind of this up, down, the background is varying, and there's a little bit of activity in here, and that's probably Jupiter. Jupiter's much, much fainter. It's about 100 times fainter than Virgo A. So imagine these bars, but 100 times fainter. They're now smaller than the oscillating background. And it's only through our statistical analyses that we'll be able to bring it out and see it. Okay. Now, what's this? Here at the end, we have all this rattiness. That is radio frequency interference, RFI, the enemy of the radio astronomer. If the moon is the enemy of the optical astronomer, RFI is the enemy of the radio astronomer. So this is civilization. Maybe it's ground-based, maybe someone flew overhead and transmitted. This is a protected frequency band reserved for radio astronomy. And I've been doing radio astronomy for over 30 years, and it used to be rare, but now it's common. In almost every observation, you have some RFI. Just the nature of advancing civilization. Eventually, at some point in the future, we'll have to put our radio telescopes out in space, pointed away from the Earth. People have talked about putting them on the backside of the moon to avoid RFI. But we have ways of dealing with it, as you'll see. The last thing to explain on this plot are these spikes at the beginning and the end. And this is a little subtle. This is calibration. And calibration is always the hardest thing to explain. Calibration's boring, but it's so important. If you don't calibrate your data, you can't use them. You can't measure anything of any significance. And with in these modules, it's actually a two-step calibration process. So let me explain this step. So this axis says power in Kelvin. That's after some calculations have been done. What's actually coming off the telescope is a voltage. You could hook a voltmeter up to this thing. When it's pointing at a bright radio source, you get a higher voltage. It's pointing away, you get a lower voltage. And the electronics are always changing. These are very tricky, sensitive electronics. I could look at a source and maybe my voltmeter says it's 2 volts. And I come back half a day later and it says it's 3 volts. And nothing's changed on the system. We haven't changed any buttons or settings or anything. It's just, it varies on a time scale of hours. And we need to guard against that. Remember, we're going to compare our target, whether it's the moon or Jupiter, to our calibration source. And our calibration source may have been taken hours later. And if the voltage output of the system has randomly drifted to something else, you won't be able to compare them. You won't be able to calibrate. So how do we deal with this? Well, what radio astronomers do is up in the receiver. You have the dish, you have the receiver up at top. They have a noisemaker, not an audio noisemaker or a radio noisemaker. You can turn it on and off, and it always spits out the same amount of radio waves. And it goes into the receiver because it's already in the receiver, and it goes through the whole system, just like signal from space. So if the system is under producing, giving low voltages, this is the radio noisemaker turned on and turned off. This will also be smaller. If this stuff is smaller, this will be smaller. If this stuff, the astronomical source, is stronger, this will be stronger. So what we do in our analysis in the next video is these brightnesses are divided by the height of the noise source signal. And you see we have 2 of them, one at the beginning and one at the end. Again, redundancy. In case one of them is busted or not working right, we can use the other. If we have them both, we'll make use of both and have an even stronger measurement. So we take these measurements, we divide by the noisemaker, and then they're stable against these hourly changes. How long are they stable? They're good for maybe about a day or 2. You really want to take your calibration data. You looked at the moon, you looked at Jupiter, and then we're looking at a calibrator, such as Virgo A, Cygnus A, or Taurus A, the Crab Nebula. You want to look at them within half a day, 2 days at the outside. This noise source calibration will give you that much time to get your calibration measurement. Okay, that's the light curve plot. Now the spectral plot, lots of stuff going on here. First of all, you see these gentle undulations. That is not astrophysical. There's not more flux at this frequency and less flux at that. This is a property of the instrument. It's very complicated electronics, and the response of the instrument undulates. You get more at this frequency, less at this. And the undulations are changing with time as well. So don't worry about the undulations. They're not real. I mean, they're real, but they're not astronomical. What we're really looking for are the blips on top of the undulations, and they are caused by different things. Let's start with this one here, 1420 megahertz. That one is astronomical. That's an emission line. Cold, neutral hydrogen emits 21 centimeters, which corresponds to 1420 megahertz in frequency. So that blip is astronomical. It's coming from cold neutral hydrogen. It's the most abundant thing in the universe. It's in all directions. So any spectrum you take, you'll see that. Any spectrum that includes 1420 megahertz. Sometimes it's a lot stronger. Like if you're looking at the plane of the galaxy, it can be quite strong. Now, we're not going to worry about that in this. That hydrogen is spread kind of uniformly across the whole image. And so we don't need to get rid of this frequency. It's not affecting, it will be background subtracted out. You'll see. What about this one? This one's at 1381. That is honest to goodness RFI. I don't know the source. I don't know if it's on the ground, but we see it a lot at Green Bank. That's what's causing this mess right here. Here, 340 seconds in, something started transmitting at 1381 megahertz. And yeah, it messes up your data, but the nice thing is it's only messing it up at this one frequency. And so we can cut it out. There's another one that's common in this band. You can see it here. It's very faint, right at 1400. We can treat that like RFI. We'll try to cut it out, but it's actually caused by the instrument. Now, the way the data processing is coded, you get a little blip at 1300, 1400, 1500, 1600, 1700. And so that's not technically RFI, but we'll cut it out just the same. This one didn't have any 1381 contamination. It does have the hydrogen line. Okay. So that's this one. Now, if you have a blip at some other frequency, you're going to need to know what it is. This one's 1381. That's 1420. There's sometimes one at 1400. But suppose you had another one. You can go to Live Spectrum, click on the magnifier glass, and you can zoom in around it and measure it. You can see this one is 1381. If you have some other unusual one, rare one, measure it, write it down, and in the next video, we'll learn how to remove it. Okay. What else? Back to the path map. You see this little circle here. You can also see it in these preliminary images here and here. That is the beam, the telescope's blurring scale. As we talked about previously, radio telescopes, single dish radio telescopes, have really poor angular resolution. They blur stuff out over this scale. And so that's that within that circle, about something like 68% of the brightness should be contained. If you were to take the circle and draw it here, it would contain about 68% of the source. A little bit more than half of the brightness is in this one beam circle. Okay, that's just showing you the blurring scale in your image. Lastly, you have preliminary images, one for each channel. It's good to just check, make sure they both look good. If one looks bad, we'll be sure to exclude it in the next step. Sometimes a channel dies and may remain dead until technicians can go and work on the receiver. Again, these are very complicated pieces of equipment and electronics, and they do break and need maintenance constantly. Like about once a week, telescope will go down for maintenance.